Hi everyone, this is Nihar. Welcome to my class. So today class we will study cantilever beam with an uniformly varying load or gradually varying load. Previously we have studied cantilever beam with an point load, cantilever beam with an uniformly distributed load, and in today class we will study cantilever with a uniformly varying load or gradually varying load. That means the load is uniformly increased or uniformly decreased, or it may be uniformly increased to a certain point and after that uniformly decreased. So you can say uniformly varying load or gradually varying load. So for that, see the figure uniformly varying load, cantilever with uniformly varying load. Here is the fixed part. As it is cantilever means one side fixed, other side free. So it is a cantilever beam AB. There is a uniformly varying load. Here is the examples of uniformly varying load. This amount is W for unit length. W for unit length. Here it is 0, here it is small w. The length of the cantilever beam is small. So this is an example of cantilever beam with uniformly varying load. So consider a cantilever beam AB. Here AB of length small l carrying an uniformly varying load or gradually varying load 0 at the free end up to small w at the fixed end. So in this 0 is here at the free end B and small w is at the fixed end capital A. So it is gradually increasing or gradually varying. So right, consider a cantilever beam AB. Consider a cantilever beam AB of length small l. Cantilever beam length is small l, carrying an uniformly distributed load bracket UVL 0 at the free end up to small w at the fixed end. So here is the cantilever beam AB cantilever beam of length small l carrying a uniformly varying load UVL, which is 0 at the free end and W at the fixed end. So now we will calculate the formula, the basic formula for shear force and bending moment at some extent or some distance. So again we will draw this is the free end and the cantilever beam AB. Here is the uniformly varying load UVL. This amount is small w for unit length. So now we will find out the formula for at a section small x. So let this dotted line is xx, which is small l distance from the free end. The section xx is present small l distance from the free end. Total length is small l. This is a small l. So we will find out the formula at xx. So right now we will find out the shear force and bending moment at x-axis, which is small x distance from free end. Small distance, free end, capital B. Here the free end is capital B. So the distance from free end to x-axis section is small x. So we will find out the shear force and bending moment at this section x-axis. So first shear force. So shear force at x-axis, that is you can say fx, equal to. So we will calculate the shear force at x-axis in this section. So this is due to the uniformly distributed load. The right hand side of the beam downward. Right hand of the beam downward means positive shear force. So plus the formula is half into x into Wx by L. This is the formula for shear force at a section x-axis for an cantilever beam with an UBL, equal to plus Wx into x, that is x square, by 2 into L, that is 2L, plus Wx square by 2L, shear force at a section x-axis. This is the equation of parabola. This is the equation of parabola. Now, after shear force, bending moment. So next, bending moment at x-axis, that is mx, equal to. Here we will see, due to the uniform distributed load from the upward, the beam bends like this. That means negative bending moment. So minus force is Wx square by 2L and simply multiply x by 3. Then the result will be minus Wx cube by 6L. This is the equation of cube. This is the equation of cube. So shear force at a distance small x from the free end is plus W into distance square divided by 2 into length of the beam, and bending moment at the same section x-axis is minus load into distance q divided by 6 into length of the beam. So this is the formula. You have to remind this formula for doing several problems. So now we will calculate the shear force at B and A, and also the bending moment at B and A, and we will draw a shear force diagram and bending moment diagram. For this, again we will draw this figure. So we will go from free end. So first shear force E will come. Right, calculation for shear force. Calculation for shear force. First one is B. So shear force at B, that is FB, equal to formula is plus W into x square by 12 plus W is how much? Same W into x square. That means the distance. So B at point B, it is the starting point. So distance is 0 divided by 2L. 2 into length of the beam is L. So 0 into something is 0. Next, shear force at A, that is FA, equal to plus there. Next, W is the load into distance. At point B the distance is 0, but at point A the distance is small l. So W into small l square divided by 2 into L is L, equal to L. L cancelled out. The rest part is WL by 2. This is the shear force. After calculating the shear force, what we will do? We will draw the shear force diagram, and after the bending moment calculation is there, the shear force diagram we will draw here. here, beam AB, length small l, load is W for unit length. So make a dotted line below A and also below B. For shear force diagram, first value is 0, second value is plus WL by 2. This is only the formula based problem. Put the formula, here the value is given, so getting the answer. So from 0 again plus. 0 and plus means above the baseline. So the baseline draw here. A, B. At point B the value is 0. At point A the value is plus WL2. Let us assume the point is here. WL by 2. Let us assume. So now, if there is an uniformly varying load between 2 points, then the shear force line becomes an parabolic curve. You must be remind that. If there is an UVL between 2 points, then the shear force line is a parabolic curve, but the bending moment line is a cubic curve. So this will be parabolic. There is the parabolic curve, and this is the baseline. Here the shear force F. 0 plus W by 2, and as it is a uniformly varying load, so the line becomes parabolic curve. After that, we will calculate the bending moment. Now, calculation for bending moment. Next, first point B, next A. So bending moment at B, that is MB, equal to, the formula is minus W XSQ by 6 into L. W is the load, X is the distance at which the load is applied, and 6L. 6 the number, L is the length of the beam. So minus W is the load, here comes the W, into XSQ, the distance at which you are calculating. That means we are calculating B. So distance is 0Q. W XSQ by 6 into length of the beam, that is L. 0 into something means 0. Next, after B, A comes. So bending moment at A, that is MA, equal to minus W XSQ by 6L. Previously we are calculating at B, now we are calculating at A. Now the distance becomes length of the beam, that is small l. So minus W XSQ, so W into X, in place of X we will write L cube, divided by 6 into length of the beam, that is 6 into L. Or it will becomes L cancelled out, so minus WL square by 6, minus WL square by 6. So we calculate the bending moment. We will draw the bending moment diagram. First value is 0, next value is minus. So 0 and minus means below the baseline. So here is the baseline A, here B. At point B it is 0, and at point A it is minus WL square by 6. Let it is here WL square by 6. Now we will know that when there is an UVL, uniformly varying load between 2 points, then the bending moment line will be cubic curve. So it is the cubic curve. Cubic curve. Baseline. Here is the baseline, and this is the cubic curve. Here is the parabolic curve, this is the cubic curve. Difference between parabolic and cubic: parabolic is slightly bent, while cubic is more bent. Cubic curve. So this is the formula and diagram for this problem. Shear force bending moment calculation diagram. Now we will solve some problems regarding cantilever with UVL. Here is the question given. Draw a shear force and bending moment diagram for a cantilever beam as shown in figure. Here figure, there will be a cantilever beam with UVL and the length of the beam is 4 meter. We will calculate the shear force diagram and bending moment diagram for this beam. So for that, first we will calculate the shear force. Answer: calculation for shear force. Calculation for shear force. So we will start calculating from the right hand side or free end. So first one is B, that is shear force FB, that is FB equal to, we know the formula, plus Wx square by 2L. So plus W means load. Here the load is 3 kN/m, the W is 3. X square. The starting point we are calculating at B. The starting point, the distance is how much? 0. So 3 into 0 square by 2 into length of the beam 2L, that is 2 into 4. 3 into multiplication 0 means all value 0. Next, shear force at A, that is FA equal to same Wx square by 2L, but now the value of x becomes from B to A, that is 4 meter. So plus W means 3 into x square. X means the distance from the free end. The distance from the free end A is 4. 3 into 4 square divided by 2L. 2 into length of the beam, that is 4. So 4, 1, 4 cancelled out. That is 3 into 4 by 2. 2, 3 is 6 plus 6 kilonewton. Plus 6 kilonewton. So now we will draw the shear force diagram. For that, first we will draw the question. A, B, kilometer per meter, length is 4 meter. Draw the dotted line below point A and point B. Now, the first value 0 and another is positive. 0 and positive means above the baseline. So here is the baseline A, here B. At point B, the value of shear force is 0. At point A, the shear force value is plus 6. Let the plus 6 point is here. So now we will study previously that if there is an UVL is there, then the shear force line is parabolic curve. The parabolic curve. This is positive sign. Make inside the curve. This is parabolic curve. This is the shear force diagram. SMD. Shear force diagram. After the shear force diagram, we will calculate the bending moment. Calculation for bending moment. Calculation for bending moment. Similarly, shear force bending moment will calculate from the free end. So starting point is B. So bending moment at B, that is MB equal to, the formula is minus Wx by 6L. Remember the formula, minus Wx by 6L. So minus W is the load, that is 3, into x cube, the distance from the free end. As we are calculating at B, so the distance is 0. Wx by 6 into length of the beam 6L, L is the 4. 0 into something means 0. Next, bending moment at A. After B, A point comes, so that is MA equal to minus Wx by 6L. So minus W means 3. X cube means the distance from the free end. So A point is from the free end how much? 4 meter. So 4 into Q, 3 into 4 cube by 6L. 6 into L is 4. Minus 8 kilonewton meter. So at point B is 0, at point A is minus 8. So the diagram means below the baseline. So here is the baseline A, here B, At point B it is 0. At point A it is minus 8. Let here 8. So when there is an UVL between 2 points, the bending moment line is a cubic chord. Cubic chord means dipole. Dipole line. Sketching will be inside. Here we will write bending moment diagram. This line is cubic chord. This is cubic chord, and these two are what? Baseline. These two are baseline. So this is the shear force diagram. That is the bending moment diagram. Here you have to not remind this. You have to only know the formula. After that, at point B it is 0. At point A it is distance. Then we will calculate the. Now we will solve another problem where a cantilever beam with an UTL and UVL, both the load will be there. Cantilever beam with an uniformly varying load along with uniformly distributed load. So write the question. Here the question is, draw the shear force and bending moment diagram for the cantilever beam. See, here is the cantilever beam, one end fixed, other end free. Here we will see from B to A up to this point, it is an uniformly distributed load. That is, the load is totally uniformly distributed. That is 2 kN per meter. But above the UTL, there is a uniformly varying load. That is 0 at this point and gradually increase up to this. So from 0 to 5, that means this uniform distributed load is 2 kN per meter. So this much is 2 kN per meter, and the rest part is how much? 5. Total is 5. This is 2. So how much is 3 kN per meter? So this is 3 kN per meter. The UVL part, here is the UVL part, uniformly varying load. This UVL part is 3 kN per meter, but this UDL, uniformly distributed load part is 2 kN per meter. Here two load is there on an cantilever beam. There is a uniform distributed load of 2 kN per meter, and above that there is a uniformly varying load of 3 kN per meter. We will find out the shear force diagram and bending moment diagram. For drawing the shear force diagram and bending moment diagram, we will calculate the shear force or bending moment at the 2 points A and B. So first we will calculate the shear force at A and B. So keep ready and start. Calculation for shear force. Calculation for shear force. So we will calculate from the free end, that is first point B, then point A. So shear force at B, we can say FB equal. Here you will see at point B there is an UDL, uniformly distributed load, which is 2 kN per meter, and above that there is an UVL, uniformly varying load of 3 kN per is there. So when we will calculate the shear force at B, first we will calculate the shear force for UDL plus for shear force for UVL. So for UDL, the shear force formula is plus W into X. So as due to the UDL and UVL, the right hand side of the beam moves downward. So right hand side of the beam moves downward means positive shear force. So for UDL 2 kN per meter, the value is plus W into X. W means 2 into X means the distance. Sorry, we are calculating at B, which is the starting point. The distance is 0. So plus 0 into 0. Next, this part is for UDL. Next, for UVL, the formula is plus Wx square by 2L. Plus Wx square by 2L. So plus W means UVL, for UVL the weight is 3 kN per meter. So plus Wx square, W means 3 into x square means starting point, distance x is 0, Wx square by 2 into length of the beam. Length of the beam is how much? 2 equal. This is value for uniformly distributed load of 2 kN per meter, and this value is for uniformly varying load of 3 kN per meter. This value is 2 into 0 is 0, 3 into 0 is 0. So total value will be. Now after B, point A comes, which is 2 meter distance from the free end. So now at point A, the value of x becomes 2 meter. Remind it. When we are calculating at A, the value of x becomes 2 meter. When we are calculating at B, the value of small x or the distance from the free end is 0. So shear force Fa, that is Fa equal to cross W into x. This is for uniformly distributed load. Here uniformly distributed load is there, uniformly varying load is also there. So for uniformly distributed load, plus W into x, W is 2 into x. Previously I have told you from at point A the x value is 2 meter. So 2 into 2 plus Wx square by 2n, that is W means 3 into, now x value is how much? 2 meter. 3 into 2 square divided by 2 into 2. How much? 2 into 4 plus 4 plus 3 7. That is plus 7 kilonewton. Plus 7 kilonewton. That is shear force at A. Now we will draw the shear force diagram. For that, first we will draw the question. A, B, this is 3 kilonewton per meter, and this is 2 kilonewton per meter, and the total from left side is 5 kilonewton per meter. So this amount is 2 kilonewton, this amount is 3 kilonewton. Next, length is 2. Next, make a dotted line below point A and point B. Here you will see, for shear force diagram, at point B is 0, at point A is plus 7. 0 plus 7 means this point will be above the baseline. So here is the baseline A, B. At point B, the shear force value is 0. That means here. At point A, the shear force value is plus 7. Let the plus 7 is here. Let. Now we will see there is an UDL there and UVL is also there. Here, so totally we will consider this is an UVL, uniformly varying load. So for UVL, if there is an UVL is there between 2 points, then the shear force line is a parabolic curve. So from B to A, we will join it by a parabolic curve. The plot sign is given and make matching line here. This is shear force diagram. This curve is parabolic curve and this line is your base line. Here you will see at point B, the value from B to A, it is gradually increasing. If the value is gradually increasing or gradually decreasing, then we can say it is an uniformly varying load or gradually varying load. Here, as the value from B to from value at A gradually increases, so we will consider the total load as uniformly varying load, and as it is uniformly varying load, like that we will draw the shear force diagram. It is a parabolic curve. Now after drawing the shear force diagram, leave some space. Below that you will calculate the bending moment. Here we will calculate the give heading calculation for bending moment. Similarly, shear force, we will calculate the bending moment. First we will calculate at B, then we will calculate at A. Now, bending moment FV, that is MV equal. Here you will see at point B, UDL is there and UVL is there. So for UDL, the bending moment formula is minus W into X by 2. Previously we have studied. And for uniformly varying load, the bending moment formula is minus WXS cube by 6L. WXS cube by 6L. So first for UDL, this much for UDL minus H, the load will be applied upward. So the beam bent like this. That means negative bending moment. So negative for UDL, that is minus W into X by 2. At point B, the value of X is how much? 0. Starting point X is 0. So W means 2 into X means 0 into X by 2 means 0 by 2. This is for uniformly distributed load. Next, there is an UDL is also there. It is the starting point of UDL. So what is this? Minus WXS cube by 6L. Here the X value is 0 as it is the starting point. So W is for UVL, W is 3. W into XS cube means 0 cube divided by 6 into length of the beam means how much? 2. So 0 into something is 0. Here we will see two values are there. First value is for uniformly distributed load of 2 kN per meter, and the second value is for uniformly varying load of 3 kN per meter. It is the formula W into X by 2, and it is the formula WXS by 6L. Here small x, the distance from the free end is 0 as it is the starting point. Next, after B, point A, so bending moment F A, we can say MA equal to. Here you say at point A, this amount is UDL and this amount is UDL. For UDL, that is minus W into X, this distance becomes X, so 2 meter. 2 into X by 2, that is 2 by 2. W into X by 2. Here at point A, X value is 2 meter because it is the distance from the free end, 2 meter. Next, minus. For UVL, the value is WXS by 6L, W is 3. 3 into X value, that is distance from the free end, how much? 2. 3 into 2 cube divided by 6 into length of the beam, how much? 2 equal to minus 6 kN meter. So the value of bending moment at A is how much? For UDL, uniform distributed load, this much, minus W into X by 2. Here X value is 2. How much? X means the distance from the free end. How much? 2 meter. So W into X by 2. The W is 2 kN per meter. Next, this value is for uniformly varying load. For uniformly varying load, the formula is minus WXS cube by 6L. So minus W is how much? 3 kN. UVL, for UVL, the W value is 3. So 3 into 2 cube WXS cube by 6 into L. W is minus 6 kN. So now we will draw the bending moment diagram. Here the value is 0 and the value is minus 6. So 0 minus 6 means below the baseline. So we will draw the baseline here. A, B. At point B, the bending moment value is 0. So this is 0. At point A, the bending moment is minus 6. Then this is minus 6. So if it is a uniformly varying load, all total we will consider because the value is increasing. Gradually increasing means uniformly varying load. Gradually decreasing means uniformly varying load. So if there is an UVL between 2 points, then the bending moment diagram is a cubic curve. Cubic curve. Cubic curve means little deeper than parabolic. Here make an arrow and write cubic curve. Always make an arrow mark and write what is this curve. If it is a straight line, you write it straight line. If it is an inclined straight line, you write it inclined straight line. If it is a parabolic curve, you write it parabolic curve. If it is a cubic curve, you write it cubic curve. So this is the bending moment diagram and this is the baseline. You have two baseline, shear curve diagram, bending moment diagram. Complete? All of you understand? So this is all about cantilever beam with an UDL along with an UVL. In the next class, we will study the simply supported beam with an point load. Simply supported beam, you must know that simply supported means that it has two supporters at the two ends. This is called simply supported beam. A beam which has two supporters at the two ends, we can say simply supported beam. So we will discuss the simply supported beam with an wire rod. Thank you for the class.